In this presentation, we will discuss our recent paper about our newly proposed computational analytics, density of atomistic states, DOAS, in understanding the frustration mechanisms in super-ionic conductors, which enable their exceptionally high ionic conductivities for energy applications, such as solid-state batteries. Solid-state lithium-ion batteries are a promising technology for next-generation energy storage. They use inorganic ceramic lithium-ion conductors to replace flammable liquid electrolytes, enhancing both safety and energy density. A key challenge in solid-state lithium-ion batteries is the development of inorganic solid electrolytes that provide high lithium-ion conductivity along with other essential properties. Therefore, there is a strong need to discover and design novel fast-ion conductor materials. Compared to liquid electrolytes, only a very limited number of solid ion conductors can achieve similar levels of ionic conductivity at room temperature. These super-ionic conductors are from diverse chemistries, compositions, and crystal structures. To develop new lithium-ion conductor materials, we must first understand the fundamental mechanisms that enable super-ionic conduction. This understanding will then allow us to rationally design novel lithium-ion conductors by computation. Here we compare a typical solid with a super-ionic conductor, garnet LLZO. In super-ionic conductors, the lithium sublattice is disordered, as evidenced by lithium site partial occupancy. Additionally, site positional disordering occurs at certain lithium sites, as shown by the lithium probability density spreading over a larger volume. As a result of this disordering, the lithium-ion sublattice contains a large number of possible lithium-ion configurations. Many of them exhibits very similar energies, that is, energy degeneracy, also known as the frustration. The increased entropy of the disordered lithium-ion sublattice enables the super-ionic transition, as illustrated in the Gibbs energy curve on the right. A key strategy for designing super-ionic conductors is to lower the transition temperature Tc by promoting frustration or disordering in mobile ion sublattices. To achieve this, it is crucial to understand the underlying frustration mechanisms of super-ionic conductors. However, a major challenge lies in the lack of computational analytics capable of quantifying, evaluating, and assessing the vast number of atomic configurations and their corresponding energy levels within a disordered lattice. For example, how the frustration and disordering change locally atomic configurations and energetics, how to quantitatively elucidate and characterize the onset and the degree of frustration in super-ionic conductors and during super-ionic transition, how ion diffusion mechanisms are changed in a disordered mobile ion sublattice of a super-ionic conductor under frustration. We need computation analytics to quantitatively elucidate and characterize these mechanisms and help answer these scientific questions. In this work, we study the super-ionic transition in lithium yttrium chloride, LYC, a promising lithium super-ionic conductor. LYC has a hexagonal close-packed chloride framework. The structure consists of alternating yttrium-rich and yttrium-poor layers, where yttrium and lithium-ion primarily occupy octahedral sites. We conduct MD simulations using deep potential and obtain room temperature ionic conductivity in agreement with experiments. A super-ionic transition is also observed in the MD simulation. As temperature increases, a transition occurs at the Tc of 425 K, converting the ordered lithium-ion sublattice into a disordered lithium-ion sublattice. The transition is shown in the Arrhenius plot on the left. Below Tc, lithium ions remain in ordered octahedral sites, thus exhibiting slower diffusion with higher EA. Above Tc, the disordering is shown by the lithium partial occupancy of both octahedral and tetrahedral sites, showing fast diffusion with low activation energy of 0.24 electron volts. Our question is, how can we quantitatively elucidate and characterize the onset and degree of frustration in super-ionic conductors and during the super-ionic transition? To answer this question, we introduce the density of atomistic states, DOAS. The lithium dose is calculated as a histogram of atomistic energies of the lithium-ion states. Each lithium-ion state corresponds to a distinct local configuration of a lithium ion with different configurations of surrounding cations and vacant sites. The dose of individual lithium ion clearly elucidates the local states of lithium ion, their energy levels, and how many of them. For the ordered lithium-ion sublattice at low temperatures before the transition, the lithium dose shows two peak states, corresponding to the two octahedral sites in the yttrium, poor and yttrium-rich layers respectively, After the super-ionic transition at temperature beyond Tc, the lithium DOAS shows that these two peak states broaden into a large variety of local configurations, or lithium-ion states, with a range of small energy differences. This plenitude of lithium states with small energy differences manifests the frustration of the lithium-ion sublattice. Thus, the lithium DOAS effectively illustrates the frustration in super-ionic conductors during the super-ionic transition. As shown in the DOAS, a large number of lithium ions on tetrahedral sites, shown in orange, are activated after super-ionic transition, in agreement with the structures observed in MD simulations. The activation of tetrahedral lithium can be explained by the greatly reduced energy barriers between octahedral and tetrahedral lithium states, as shown by the overlapping among broadened energy levels of octahedral and tetrahedral lithium states. The increase of tetrahedral lithium states, in turn, leads to a large variety of local cation configurations of octahedral lithium states, thus promoting disordering and frustration. In summary, the DOAS unravels how the super-ionic transition and frustration are caused by the changes of local configurations and energetics of individual atoms. The mechanisms of lithium-ion diffusion can also be illustrated and analyzed as the transitions among lithium states in the lithium DOAS. The HCP chlorine anion framework of LYC has two diffusion pathways, octahedral to octahedral channels along the C-axis, and octahedral to octahedral pathways connecting the C channels to create 3D diffusion networks. In the ordered Li-ion sublattice below Tc, lithium-ion migrations along the octahedral to octahedral pathways correspond to transitions between the two octahedral lithium states in the lithium DOAS. This pathway cannot percolate without the formation of an extra lithium vacancy, which has a high formation energy. For the octahedral pathway, lithium-ion migrates through intermediate tetrahedral and octahedral sites, shown as the small high-energy states in lithium DOAS, which exhibits a high-energy barrier of 0.46 electron volts as calculated by the nudged elastic band NEB method. Therefore, in the ordered lithium-ion sublattice, lithium-ion diffusion is impeded by the lack of percolation among the limited number of accessible lithium states as illustrated in lithium DOAS. How does the frustration of the mobile ion sublattice enhance ion diffusion in super-ionic conductors? As elucidated by the lithium DOAS above Tc, the disordered lithium sublattice contains a large number of tetrahedral and octahedral lithium states, each with distinct ion configurations and a range of broadened energy levels. Due to this large number of local lithium configurations, many octahedral lithium ions have more vacant octahedral sites nearby as a result of disordering and the activation of tetrahedral sites. This opens multiple local diffusion pathways for ion hopping and enables long-range percolation throughout the crystal structure. As observed in MD simulations, the transitions between these lithium states, representing lithium-ion migrations, exhibit significantly lower energy barriers. This occurs because the broadened energy levels of tetrahedral and octahedral lithium states partially overlap, reducing the energy gaps. Lithium-ion migrations along octahedral to octahedral pathways are calculated to have low energy barriers, ranging from 0.03 to 0.25 electron volts. Similarly, octahedral to octahedral pathways also exhibit low barriers of 0.08 to 0.24 electron volts due to the overlapping of broadened octahedral lithium states. With a large number of possible ion hopping pathways and significantly lower energy barriers, many of these transitions become dominant because they are thermally activated with an exponentially higher probability, leading to an overall low activation energy for lithium-ion conduction. In short, the broadening of ion states induced by frustration effectively reduces energy barriers for ion diffusion, as revealed by the DOAS. Here we show how we can design new super-ionic conductors by facilitating frustration guided by DOAS. As we just showed, in the original LYC, the activation of the disordered sublattice is governed by the transition between certain lithium states. To facilitate this, one design strategy is to introduce higher energy states. Another strategy is to broaden the states of mobile ions. As a result, these induced mobile ion states have narrower energy gaps to the activated states, thus yielding lower activation energy for super-ionic transition and ion diffusion. Now we will demonstrate these design strategies in the LYC material by modifying the cation or anion sublattice. Here we demonstrate the design strategy 1 in a PNMA polymorph phase of LYC with identical HCP chlorine anion sublattice but a different yttrium cation sublattice, which are experimentally known. The original LYC is shown on the left for comparison with its Arrhenius plot and lithium DOAS during super-ionic transition. As illustrated by the lithium DOAS, new octahedral lithium states with higher energy levels are introduced by the distinct yttrium cation sublattice. These new octahedral lithium states have narrower energy gaps to tetrahedral lithium states, facilitating the super-ionic transition. As shown in the MD simulations, the PNMA phase exhibits super-ionic transition at a lower TC of 380 K. The narrower energy gaps, as shown in lithium DOAS, also yield lower energy barriers for lithium-ion diffusion, in agreement with the lower activation energy and higher RT ionic conductivity observed. For the design strategy 2, we achieve it using mixed anion substitution to induce diverse local anion coordination of lithium sites, which are broadened to a large number of lithium states. A candidate LYBC is created by randomly substituting 25% of chlorine with bromine in the original LYC, shown on the left as comparison. In LYBC, the octahedral lithium states with a variety of mixed chlorine-bromine anion coordination exhibit a broad range of energy levels as observed in the lithium DOAS. A large fraction of broadened octahedral lithium states have narrower energy gaps with tetrahedral lithium states, facilitating activations to disordered states and leading to lower diffusion barriers. The mixed anion LYBC has an even lower TC of 360 K and a higher lithium ionic conductivity at room temperature, significantly higher than the original LYC. With our experimental collaborators, Professor Hailong Chen and Dr. Ju Liu, these mixed anion halide materials are demonstrated with lower TC and much higher conductivities. The highest reported lithium-ion conductivities in halide solid electrolytes are achieved by our design strategy. In summary, we demonstrated DOAS in guiding the design of new super-ionic conductor materials. 2 design strategies, 1 introducing higher energy states and 2 broadening the states, are demonstrated through the modification of the cation or anion sublattice in LYC. The DOAS also helps us understand other mechanisms that cause frustration, including distorted sites, geometric symmetry, and anion rotation, as discussed in other SICs. In prior computational studies, the crystal structure frameworks of lithium super-ionic conductors have been found to feature lithium sites that are enlarged or distorted. These enlarged sites allow multiple positions for mobile ion occupancy, thus broadening the mobile ion states as shown in DOAS. Similarly, the distortion of the mobile ion sites increases the site energies for the mobile ions. The design strategies that enlarge and distort mobile ion sites have successfully led to the development of new ion conductors. Our DOAS provides a unified physical picture to illustrate and understand a variety of frustration mechanisms across many materials and to design new materials. In conclusion, we propose and demonstrate the density of atomistic states, DOAS, as an effective analytics for unraveling the disordering mechanisms in atomistic systems, such as the super-ionic transition and frustration of the mobile ion sublattice in super-ionic conductors. DOAS has several unique strengths. 1. DOAS quantitatively characterizes the onset and degree of disordering. For example, during a super-ionic transition, DOAS shows the broadening of atomic states and a large number of locally disordered atomistic configurations with similar energy levels. 2. DOAS reveals the atomistic mechanisms that cause frustration and disordering. For example, the super-ionic transition in LYC involves the activation of tetrahedral lithium sites, and in LYBC it is facilitated by the high energy states of mixed anion coordination. 3. DOAS elucidates diffusion in the frustrated ion sublattice of SiCs as the transitions among the broadened energy states of mobile ions with narrowed energy gaps. DOAS can be further generalized and utilized for a wide range of phenomena. The DOAS can be further generalized and utilized for a wide range of phenomena, including amorphous materials, phase transitions, nucleation and growth, complex fluid systems, and high-entropy materials, in which locally disordered atomistic configurations and energetics play crucial roles in the physical properties and processes. For example, high-entropy mixing of multiple elements in the material may cause extensive broadening of atomistic states, which have been demonstrated in designing super-ionic conductors. We look forward to further science advancements made by using DOAS.